Every smartphone, computer, and digital communication system processes signals digitally. But the real world is analog. Sound, radio waves, and sensor measurements all exist as continuous signals. How can a continuous signal be converted into discrete digital samples without losing information? The answer lies in the sampling theorem. Most physical signals in nature are continuous. A microphone produces a continuously varying voltage, an antenna receives continuously changing electromagnetic waves, and sensors generate analog outputs that vary smoothly over time. However, modern communication and computing systems process information digitally. This creates a fundamental challenge. Computers cannot directly store or process continuous signals. Instead, they require discrete numerical values. Engineers therefore need a method for converting continuous time signals into digital representations while preserving the original information. The critical question is how often the signal must be sampled. If too few samples are taken, important information may be lost. If too many samples are taken, unnecessary storage, processing power, and transmission resources may be consumed. The sampling theorem provides the answer. The sampling theorem states that a band-limited signal can be perfectly reconstructed from its samples if the sampling frequency is at least twice the highest frequency contained in the signal. This minimum required sampling frequency is known as the Nyquist rate. If the sampling rate meets or exceeds this requirement, the original continuous signal can theoretically be recovered without any loss of information. The theorem provides one of the most important connections between analog and digital systems. It establishes a precise mathematical condition under which continuous signals can be represented using discrete samples while maintaining complete information about the original waveform. Intuitively, imagine recording the position of a moving car. If you take a photograph every few seconds, you can estimate the car's path. However, if the photographs are taken too infrequently, important details of the motion may be missed. Sampling a signal works in a similar way. Physically, consider an audio signal containing frequencies up to 20 kHz. According to the sampling theorem, the signal must be sampled at a rate greater than 40 kHz to ensure that all information can be reconstructed accurately. This is one reason why audio CDs use a sampling rate of 44.1 kHz. Mathematically, sampling converts a continuous signal into a sequence of discrete values measured at specific time intervals. If the sampling frequency satisfies the Nyquist condition, these discrete samples contain sufficient information to recreate the original continuous waveform. Sampling plays a central role in modern RF engineering because nearly all communication systems rely heavily on digital signal processing. Signals received by antennas are often converted into digital form before filtering, demodulation, decoding, and analysis occur. In software-defined radios, high-speed analog-to-digital converters sample RF, or intermediate frequency signals, and transfer them into the digital domain. The quality of this conversion directly affects receiver performance and system accuracy. At the system level, sampling influences bandwidth requirements, data rates, storage capacity, processing complexity, and hardware design. Choosing an appropriate sampling frequency is one of the most important decisions when developing modern communication systems. The sampling theorem assumes that the signal is band-limited, meaning it contains no frequency components above a certain maximum frequency. Real-world signals often require filtering before sampling to satisfy this assumption and prevent unwanted effects. A common mistake is believing that any sampling rate can accurately represent a signal. In reality, sampling below the Nyquist rate introduces errors that cannot be corrected after the fact. Once information is lost during sampling, it cannot be recovered later. The sampling theorem naturally leads to the next important topic in signal processing, aliasing. Understanding what happens when the sampling rate is too low helps engineers appreciate why the Nyquist condition is so critical in digital communication systems. In this lesson, we learned that the sampling theorem defines the minimum sampling rate required to convert a continuous signal into a digital representation without losing information. We also saw how the Nyquist rate establishes the connection between analog signals and digital processing systems. In the next lesson, we will explore aliasing and discover what happens when signals are sampled below the required sampling frequency. If you found this useful, like the video, subscribe, and follow for the next lesson.